Hey guys, hoping you were able to just watch the lab there. Where we ran through the 421 logic. Um, it's going to finish up the lecture for the third you know distribution class. I apologize. Last time it seems that I had good audio, but the video didn't quite work as well. So I apologize for that. I hope you guys were able to follow the audio, alongside the PowerPoint on your own, and you know, able to have a feel for what slide I was referring to, and keep up with it. I did receive at least one request to go back over the cold load pickup logic. I definitely understand that logic is a bit tricky. So we can do that today. I also want to take some time to go over an Excel spreadsheet that I put together to help you guys with the homework that can be used to mimic, what you might do in Aspen one-liner, but you don't require a license for. So I think last time we left off on fuse saving schemes. Fuse saving scheme, as a reminder, is a fast relay curve that's intended to operate before a fuse minimum melt curve on the first trip attempt or first shot, or say 0th shot. And then, that's intended to just, save the fuse, save a technician from going out and replacing the fuse. And then as you get further along into your reclosing sequence, you move over to that slow curve where the fault is more likely to be permanent, and that allows the fuse to isolate it, and for the relay to not trip and potentially save some customers from losing power. So that's the fuse saving scheme in a nutshell. As a recap, the sequence coordination is really intended to address the situation where we have two fuse saving schemes in parallel. We can see here, for example, relay 1, which trips the breaker, may want to have a fuse saving scheme with fuse 1, and then recloser 1 may want to have a fuse saving scheme with fuse 2 and fuse 3. So we can see here, we could set up relay 1 to have, a fuse saving scheme with fuse 1. And then we could set up relay 1 to also have, coordination with recloser 1. We can see here that curves 1 and 2 are for the relay fast and slow curves, respectively. And then curves 3 and 3F would be the fast and slow curves, respectively, for the recloser. So it's kind of weird to show here. We've got two separate curves set up for the relay. But then in Aspen, if you actually tell it it's a recloser controller, it automatically creates that F designation, like the 3 and the 3F for you. So we can see that. But the basic principle here is, let's say we had a permanent fault on the X. Well, in that case, recloser 1 is going to trip on its fast curve, and then relay 1 is not going to trip, right? Which is good, because we don't want people, the load off of fuse 1 to lose power, and it can be isolated by the recloser. So that's a good thing, right? Recloser 1 tripped, the relay didn't. Now, eventually, right, recloser 1 is going to move to its slow curve. And unless we intervene, relay 1 is going to stay on its fast curve. Now, if that happens, if the relay stays on its fast curve, curve 1, and the recloser moves to its slow curve, which is curve 3, then the relay is actually going to trip faster than the recloser, and the load off of fuse 1 are going to lose power when they didn't have to, and it could have been prevented. So the way that we address that is we are going to have something called a skip shot. When the skip shot occurs, we're going to set up the relay to skip a shot whenever the relay picks up, rather than when there's a reclose initiate based on a trip. So what would happen here, if we can coordinate this with our reclosing, is that fault would happen, on the designated X point that we have here. The recloser would trip. The relay wouldn't trip, but it would actually pick up. And when it picks up, it would skip a shot in its reclosing cycle. So both the relay and the recloser would go from shot 0 to shot 1. And they would be able to increment in sequence with each other, so that they can stay on the same page. So that when recloser 1 moves to its slow curve, relay 1 can also move to its slow curve. In the two time current curves, curves 2 and 3 can then coordinate. When we can pull that off, the customers off of fuse 1 aren't going to lose power. Recloser 1 can isolate the fault like it's intended, and the breaker being tripped by relay 1 can stay closed, and everyone's happy. So that's the basic principle. I don't have any example relay logic for it to show you guys right now. It's I guess it's quite or it is quite involved, more so than the cold load pickup logic. So I left that out. There's also another scheme, not to be mistaken with sequence coordination, that's becoming very popular in Maine, called sequential reclosing, that I left off of here. Like I said, not to be mistaken with sequence coordination. But the sequence coordination is just a way where both the recloser and breaker will trip, and then whatever's got a hot bus deadline will reclose. So the breaker would close, but it would not immediately trip back out. After a certain period of time, recloser 1 would reclose on its hot bus deadline, and then it would immediately trip out. The only difference is the reclosing cycle would be on a fast curve to prevent relay 1 from also tripping. So that's starting to become a pretty common scheme as well. So we'll leave it off here. There's kind of ways to accomplish these things. So moving on from sequence coordination, we can move over to distributed generation. This is becoming huge. I think in the state of Maine right now, I think there's literally hundreds of generation proposals out there, to be tied into our distribution system. I'm sure you guys can see that. You drive down the road, they're everywhere. Seems like they're putting a couple acres of solar on any patch of grass they can, really. It used to be, mostly rotating machines, but we're getting into a world of solar, battery, wind, where these inverters are actually starting to dominate. I have seen rotating machines on distributed generation, but it's really starting to become the minority. And by rotating machines, synchronous generators, induction generators, being driven by a prime mover, maybe like hydro or biomass or something like that. I probably wouldn't say coal or oil or nuclear or anything like that. Those would all generally be connected to the transmission system. But some of those smaller hydros, things like that, might be on a distributed generation network. As I mentioned, the battery storage is also becoming extremely popular. That helps fix the challenges between peak generation times not aligning with peak demand times. Right? It's sunny during the day. Let's say in the wintertime it gets dark, around 5. So solar is not going to do you much good at 6 when everybody gets home and turns the electric oven on all at the same time. So there's actually battery storage projects out there that actually just charge all day long at a certain rate, and then discharge when the demand is high at a higher rate. And that's how they make a profit. So it's becoming a popular thing. So these distributed generation sites are typically under 10 MVA. Larger than 10 MVA requires some more stringent regulations, modeling, things like that, studies. So they're usually under 10. And then in Maine, these sites are generally owned by independent investors and not the utility themselves. That's not the case everywhere. It is kind of most places, but there's a thing called deregulation in the state of Maine that kind of separates the utilities and the generation. So like a Central Maine Power or a Versant typically wouldn't own those solar facilities. Those are usually owned by independent power producers that sell the power to the utility. So like I said, not the case everywhere, but in the state of Maine, that's usually the case. Some more on distributed generation, a term penetration level, the rated power output of the distributed generation over the peak load. So for example, if you had 1 MVA of distributed generation on a line with a peak loading of 10 VA, penetration is 10%. Generator step-up transformers, commonly called GSUs, may or may not have high side windings, which would be an additional ground source in the distribution circuit. Can have certain impacts. And then one major consideration, especially in our protection world, is knowing that inverters have built-in anti-islanding functions, meaning that they usually can't operate when they become disconnected from the grid. That is, utilities lost. They actually usually will turn themselves off in under 2 seconds. Something may not have been thought of at first when it wasn't as popular, but challenges are actually starting to occur with the magnitude of inverters that we have out there, where their algorithms are so proprietary that one inverter manufacturer can't tell if it's islanded if it's connected to a different inverter manufacturer, right? It can't tell the difference between the other inverter and a normal grid. So we're starting to run into challenges where having multiple inverter manufacturers on the same circuit may actually hold each other up and prevent the anti-islanding functions from working and forcing them to turn themselves off in under 2 seconds. So that's starting to become, I guess, a challenge. So this may be a typical arrangement they might see. This comes off a 12 kV substation bus. It's got a breaker. It's got a relay. You can see there we got the backbone, the distribution circuit with our typical things that we've been talking about. fuses, reclosers, load. And then we can see we've got a generation recloser. And then we have a point of demarcation, goes between what's utility owned and then generation owned. This one has a fuse going to a GSU that goes to an inverter. So just a good visual of a typical trend. So some inverter fault characteristics. The fault characteristics are a lot different than rotating machine characteristics. The big difference here is the lack of inertia and stored energy. It also has a lot to do with the fact that what's driving these inverters are more based on programming, it's software and firmware, than it is the power electronics, based more on all of those things than just natural laws of physics, which is what drives our conventional thought process with with symmetrical components, things like that. So one consideration is many inverters do not source zero sequence current. They're actually usually separated by a delta Y transformer, at the pad mount level. That goes from low voltage to medium voltage. So usually separated on the zero sequence. If we want to add a ground source from a transformer with a Y grounded winding up on the distribution side, we can do that to kind of fix that problem. The second bullet point I may want to maybe reword. Many inverters do not source negative sequence current. That may be true for many inverters, but many inverters produce what I would call a unreliable and unpredictable negative sequence current. That really can't be used reliably in the way that rotating negative sequence quantities are used. And then most inverters don't contribute a ton of fault current. So like a typical inverter might produce at most 130% of peak load for a short circuit condition. It's a little bit tougher to distinguish that type of fault characteristic as compared to a rotating machine, which may produce 600-700% of peak load. Right, it's easier to tell the difference between load and faults. So when those two are close, like they are with inverters, those are tougher. So with all of these considerations, protection in inverter-based systems can be more challenging. And it's for some of our older guys in industry that have been doing it for 30, 40 years, it is a total change in thought process for them, because their entire career has been based on rotating machines and those types of characteristics. So it's a challenge. Actually seems to be an easier challenge to overcome for us younger guys that haven't spent as long thinking a certain way. But definitely challenges nonetheless. So some utility considerations out of these inverter-based resources, these renewable generation sites, how do they affect things? So we are adding to the fault duty of the system. Maybe we had a system with 5,000 amps. Now the fault duty may be 6,000 amps. Studies need to be done to ensure that the equipment on that system can handle that increased fault magnitude. Things like breakers, switches, damage curves on transformers, and cables, overhead conductors, bushings. All of these things can only handle so much fault current, so those need to be looked at. Instantaneous overcurrent elements need to be checked to make sure that they don't overreach, right? If something was set to 5,000 amps, well, now we're having more than that. It may trip when we didn't previously intend it to. The GSU has a ground source. The 3I0 current may be reduced in certain branches depending on the fault location, even though the total fault current has increased. So the 51G pickups actually may need to be evaluated to assure sensitivity. That's a tougher one to maybe visualize. So let's say this here is a Y grounded winding. Let's say delta over there. The fault were to occur right here. We're going to have some 3I0 go this way, and some 3I0 go this way to that fault. Now, because of this ground source, the total fault magnitude going into the X has increased, right? But we've now created a current divider. Some of it went through this winding, and let's just say at this station. You know, we had delta Y. Some of it, you know, we'll go through this, will be sourced from this Y winding. Well, that current divider has actually pulled some of that magnitude away from this source. And although the total fault current has increased into that X, the amount of fault current that went through this breaker has gone down, which means we may need to reevaluate the sensitivity of that ground overcurrent element. So that's a consideration. So some other things we haven't talked a lot about, but line voltage regulators and low tap changers may need to be adjusted if line drop compensation is used, or if backflow is possible. I don't want to get too deep into that. Fault current can now flow in both directions. It should be evaluated if we want to use directionality. Can't use negative sequence directional elements very reliably, so we'd want to look at you know, a zero sequence polarized, or we may just want to bump the negative sequence pickups above what the inverter can put out. And if reclosing has open intervals less than 2 seconds, use a sync check may be needed to evaluate, may need to be evaluated. And then lastly, it should be checked to see if distributed generation already exists on the distribution line, and if they are from similar manufacturers. So, you know, that's becoming a pretty typical check, right? We want to make sure that multiple inverter manufacturers are going to be out on the same circuit. Because if that was the case, then they may hold each other up and prevent the anti-islanding functions from operating. And if that is the case, we may need to consider direct transfer tripping. So that would be a situation where, you know, if the breaker, you know, at the head of the feeder were to trip, it would automatically send a direct transfer trip to those reclosers at the IBR location to take them off of the circuit and prevent that islanding occurring. So these are all considerations, you know, that need to be thought through. With all of these distributed generation sites that are going into service, this is keeping us pretty busy. You know, these are all things that are being thought about on a case-by-case basis. So, I guess some new additional considerations I didn't have on here, but modeling is becoming a big consideration. I'm finding As I work on my transmission systems, a lot of these smaller sites aren't being modeled in short circuit systems, which is fine, right? Small inverters, doesn't have a big impact on the transmission system. But there's a ton of them. And as a collective group, they do have a bigger, footprint. So I'll be interested to see if more stringent modeling regulations come. And then modeling software is also struggling to keep up with these, these fault characteristics as well. Like I said, rotating machines been around for a long time. Their fault characteristics are well known, well studied, very predictable. Inverters, not as much. How do we model that? It's becoming another challenge. Programs like Aspen One-Liner have come a long way with things like converter-based resources, type 4 wind, modeling that act more as voltage controlled current sources. But it's still not perfect. It doesn't give you a dynamic picture. It gives you a steady state picture, and doesn't really give you the whole picture for what you're considering. And I'm wondering another consideration on how this is going to affect, relaying technology. The relays that we use today are all based on phasers. That is, when things happen, everything is based on a magnitude at an angle, right? 5 amps at 80 degrees. Right, they're based on phasers, and they're based on symmetrical components. As these inverters become more and more popular, I'll be interested to see if relays have options to maybe not operate off of sequence components and phasers, but really operate off of a time domain based signal, and what type of characteristics it can derive from those types of signals. So, you guys are coming in right at the perfect time to get into this. We're not going to be bored anytime soon because of this. So some additional resources related to distribution protection. We've got the IEEE standards up there first. There is a guide for applications to distribution lines. There's IEEE guides for automatic reclosing, which we've spent a lot of time on today. There's IEEE guides for interconnection requirements for distributed energy. I don't have it on here, but there is going to be a new IEEE guide for large scale solar and inverter based generation. I don't know if it's been released yet, but the industry as a whole is expecting it to have a big impact on what we do. Guides for distribution impact, system impact studies, and then a few books, based on distribution engineering. And lastly, SEL. They've got some great instruction manuals, great application guides, white papers, a lot of really great information that's free and readily accessible. That teaches you how to use their product, but also teaches you about overlying principles and like that. So that concludes what I had for a presentation there. I did want to take some time to go over the 2 Excel spreadsheets that I gave you guys for your homework. We've got a relay to relay coordination tool, and then a relay to fuse coordination tool. We'll start with the relay to relay one first. So this is really intended to mimic what Aspen does. Aspen is a super user-friendly program that has quite expensive licensing fee. It is probably the most common tool used in industry for protection studies. This is just a super basic Excel spreadsheet that I threw together that tries to copycat it and has nowhere near the functionality. So what you can do here on this blue portion is model a relay. What you can do here on the orange portion is model a relay. And then this here is intended to be the fault magnitude. The colors line up, right? Blue lines up with blue curve, orange lines up with orange curve, and red lines up with the red fault. This gives you the operate time in seconds for relay 1, relay 2, the time difference. These are just relay times. It doesn't include any type of breaker operation time or anything like that. And if you want to disable the 50, just put an NA in there. And the breaker operate time, those aren't in Aspen either. So this is actually consistent with Aspen that way. So let's say, for example, your relay didn't have a CTR 400, it had a CTR of, say, 400. You can plug that in, you see how the curve moves. Let's put it back to 240, just to get things simplified here. Our 51 pickup in amps secondary is currently set to 1. If we were to increase this, we would see this inverse time of the curve move to the right, but also move up. So let's say I punch that to 1.5. We can see that there, it moved to the right, but it also moved up. We've got our curve selection. Right now, we've got a U4 curve selected. If we wanted to, we could change that to a U3. A U3 being very inverse, and a U4 being extremely inverse. And the more inverse it is, right, it has to do with that vertical characteristic. So we could see as we go from very inverse, as we move to extremely inverse, we'll see that get just a little bit steeper. As such, right? Fairly subtle, but noticeable, right? If we go the other direction, it becomes less inverse. We got the time dial. The time dial is intended to move the curve strictly up and down. So right now we're at 5. If I move it to 8, we'll see it moves up. If I want to move it to 2, we'll see it move down. We'll put it back to 5. The general consideration here. We've got the instantaneous pickup here. That's this vertical portion of the curve. As I increase it, it'll move it to the right. With the fault current to the right of the instantaneous element, that means it will operate instantaneously, which is the case right now, right? The fault current is to the right of both of our instantaneouses. We can see both of our relays are going to operate instantaneously, and there's going to be no time difference. But if I wanted to move this out to, let's say, 20 seconds, or sorry, 30, we can now see, okay, that fault lies on the inverse time portion of our curve, and now the operate time is about half a second. And there's about a half-second difference in operate time between the two of these because you know, our other one still operates instantaneously. We can see here, you know, both of our 50 and 51 pickups are in amps secondary. So if you wanted to convert that to amps primary, you know, you just multiply times the CTR. Let's say I want to move this back over here. So right now we're operating instantaneously or without delay, if you would, because nothing's instantaneous. If we wanted to put an intentional delay in here and make it a definite time over curve, over current curve, we could do that. We can see that here. Let's put in a, we'll go a 30 cycle delay. That's half a second. But we can see that characteristic now. That line now becomes amps, set to half a second. We can see here our operate time is half a second. So I'm going to put that back to 0. As we said, we can set it to NA. That'll turn it off. Ooh. Interesting curve there. Doesn't look quite right. Yeah, that looks a little better. I think it's just the granularity of so yeah, it's starting to look more right as we push it out. All right. So I'll put a 10 back in there. Put a 1 back in there. Get that back to the base. And then lastly, this over here, we can see here this red line is about 5,000 amps. If we wanted to, we can move that out to 8,000 amps. We can move it into 2,000 amps. Move that fault around. So basically, what we'll be using this tool for in your homework is to coordinate 2 relays, right? I'm going to give you, we're going to set up a set of settings for an upstream device and a downstream device, and we're going to want them to coordinate with a certain time margin for a certain fault. So let's say this was it, right? Let's say we had set up device 1 as such, and we were trying to reconfigure device 2. With that time dial down, so we actually have a challenge here. There we go. Okay. So let's say we had device 1 configured as such. We needed to alter device 2 to maintain a certain time difference. And we knew that the fault magnitude was going to be 2,000 amps. Let's say our client has specified that they need 300 milliseconds of the time difference, right? That accounts for things like breaker operate time, the actual contact on the relay, how long that takes to physically move. It has to do with errors, how the relay is able to read current magnitudes, right? We've got, the relay converts that current to a value that it reads. It's not a perfect reading every time. Even the CT doesn't give you perfect currents. And then, there's errors in modeling. There's all sorts of potential errors, right? That time difference and wanting it to be so big is intended to overcome those potential errors. So 300 milliseconds is a pretty common time difference that you might want. Well, let's get these to coordinate. Right now, relay 1 operates in 765 milliseconds. Relay 2 operates in 923 milliseconds, and the difference is only 158. Not good enough. We want 300. Well, let's try bumping this time dial from 2.5 up to 2.75. Okay, we can see this moved a little bit. We can see we're up to 250 milliseconds. We're getting there. Let's go up to a time dial of 3. Okay, so now we're up to 342 milliseconds. Perfect. Okay. Some other things to consider is, let's say these relays were great, right? Everything coordinates, everyone's happy. Let's say 5 years later, we come back and we realize, wow, this, the grid has become a lot stronger. Now we don't have 2,000 amps anymore. Now we've got 2,500. I'm going to move these out just so we can see it. Okay, so now the system is going to contribute 2,500 amps. well, crap, now our time difference is no longer 300 milliseconds like we had wanted. We're going to have to reevaluate that again. So let's try a time dial 4. Just about there. We'll do 4.1. Okay, with 4.1, we get our 300 milliseconds of separation. So the tool is meant to be used for coordination. Like I said, it's quick and dirty. Simulation of what Aspen can do. This one's intended to be relay to relay. We also have another one over here, is intended to be relay to fuse. So we can see here, try zooming out, our blue curve is our relay, which will trip a breaker. Our orange is actually a fuse curve. It's the total clear time here. It would have been tough for me to put a minimum melt into Aspen, so I didn't do that. And again, breaker trip times don't include things like breaker operate time and such, which, like I said, just like Aspen, it's fairly realistic here. So here, I just have one curve. Could have made a fancier Excel spreadsheet that had all sorts of different fuse types, but it's just one fuse type. But you can change the size of the fuse. So this is a 200K fuse. You can change it to a 100K fuse, and the characteristic will change, accordingly. And then just like the other one, you can change your fault magnitude. You'd want to plug an NA into your 50 pickup to get that to operate, or to get that to be disabled. Same thing, we've got delays and such. So this one is very similar to the other one. So I hope that helps you, with your homework. And then lastly, almost forgot, cold load pickup. We said we were going to go back over that. Sorry if we run just a little bit over. But this, I guess, was requested. Where is the cold load pickup? Is that it? There's the cold load pickup. Okay, so to run through this again, let's think of an initial condition. The breaker is closed. The breaker's been closed for a long period of time. Cold load pickup is off. So we'll call that our initial condition. Cold load pickup off, breaker's closed, right? Feeding load, and it's been closed for a long period of time. So in this situation, we'll come through here. The breaker closed, this will be a 1. We'll have a 0 at this point of the logic. We don't have to worry about that. Come down here. We'll have a 0 here and a 0 here. So nothing is being asserted. Nothing's driving this latch, and it's off. So let's say the breaker opens. When the breaker opens, this becomes, oh, sorry, I had that wrong. Going back to breaker close. Breaker close, we have a 1. Because we have a 1, we have a 0, nothing happens here. We come down here, we have a 1, and our current is below our minimum pickup, so we have a 0. This becomes a 1. If that happens for 900 cycles, this will have a rising edge trigger. It will hit the reset, but that won't do anything because it's already off. And then same thing here, we have a 1 coming here. With the breaker being closed, if this was on, which it's not, you would reset it. But with this being off, that'll be a 0, so it can't do anything. So sorry I had that wrong the first time. But the general thing I wanted to get across there was breaker closed with cold load pickup off, nothing's going to happen. So the breaker opens. When that breaker opens, we're going to have a 0 here. We're going to have a 0 at this gate, 0 at this gate. Nothing's going to happen with this logic because we have zeros at those AND gates. With that, with that 0, we're going to have a 1 right here. Because this isn't being driven, we're going to have a 0, which comes up to this NOT gate is a 1. So if that's the case, if this breaker is open and this part of the logic isn't being driven for long enough, 10,008, what was that, 108,000 cycles, however many minutes that is, maybe it's 15 minutes. If the breaker is open for 15 minutes, essentially, we are going to send a rising edge trigger, and as long as cold load pickup is off, it'll turn itself on. So cold load pickup is on, and we'll call it armed. Now with it armed, it'll stay armed, and it really won't do anything unless that breaker closes again, because there'll be no current flow if the breaker is open. So breaker's been open for a long period of time. We've given that load time to get cold, right? Your house has physically gotten cold, let's say. When we go to close that breaker back in, now cold load pickup is on. So we close that breaker in, and we're going to have an immediate spike in current, more current than the normal pickup, let's say. What happens here is we have this overcurrent element set. If the pickup is above that normal pickup, it'll prevent this guy from timing, because it knows that we are above that normal threshold, and we're actually experiencing that cold load, the thing that we don't want to fault strip for. What will eventually happen is that current will come back down, and when that current comes back down, this pickup here will deassert, it'll go through that NOT gate, and this timer will start timing. So what we've seen for, let me get a pen here. So what we've seen for the current is this 50 P1 is the current went up with that cold load, and then as things start to warm back up, it slowly starts to drop off. And we've got that level right there, our 50 P1. We've also got a 50 P2, which will be up here. All right, because if the current's extreme enough, an R, that should have been a P. Yes. If the current's extreme enough, we do want to trip regardless of this cold load pickup logic. So that one was set at 1.4, that one's set up at 1.9, just a bit higher. So what'll happen is that current will go up because of the cold load, and then things will warm back, things will start to warm up and that value will drop. But once that value gets below this 50 P1 value for 90 cycles, it'll actually reset itself. And cold load pickup will turn itself off. And we go back to our normal state. So that'll happen. And then let's say that doesn't happen. Let's say we hang out up here for a long period of time. Let's say it's an actual fault, right? It's not cold load that's causing this higher magnitude. It's actually a fault value. But we can't make that, we can't allow that situation to hang out forever. So in that situation, cold load pickup will actually have a maximum amount of time that it can be on before it resets itself. So if it's on with the breaker closed, that situation can only happen for a period of time before it automatically resets itself, regardless of if it's above or below our 50 P. So that's kind of the basis of the cold load pickup logic. We would have an LED to let us know the cold load pickup is active. And then the way that this works is if cold load pickup is off, we would have a 0 right here. That 0 is going to go to this NOT gate, become a 1, which will allow it to pass through. And if cold load pickup is off, we'll have just our normal torque control. And we'll have our normal curve, right? We'll just have a normal curve with a pickup of 1.4. Well, if cold load pickup is on, we come through here, that 1 becomes a 0. We don't pass through that part of the OR gate. Now we have to be up above our 1.9 to get through this OR gate and allow the torque equation to work. So we'll essentially snip off part of the curve there at 1.9 amps. The curve will remain unchanged, but only the portions to the right of this line will be allowed to operate. And then, of course, as the overcurrent element operates, it'll hit the trip equation, it'll trip the breaker, and such. So I'm hoping that helps. If you guys have any questions, you can reach out. But I appreciate you guys following along this semester. Hope to see you guys maybe someday in person or in industry. So thank you.